So, the program will be as follows. So, the program is first you will define program. So, define integral f d mu. So, integral f d mu for simple functions, what are known as simple functions. So, I have not told you what a simple function is either, right. I will tell you that. So, this integral f d mu is over the whole space, okay. Then define f d mu for non-negative f, non-negative measurable f, okay. And then you define it for general for arbitrary measurable f. F is always measurable, okay. Arbitrary f. Then finally, so finally we will define integral over a f d mu. Once we have defined integral f d mu over the whole space, we will finally define integral over a f d mu, okay. Okay, this is the program we will follow. First for simple functions, for then for non-negative f, not necessarily simple, then we will define it for arbitrary functions, not necessarily non-negative. Then finally, we will define integral over a f d mu, okay. So, let us first so let us just first define integral for simple functions. It can be written as f of omega equal to sum over I equals 1 through n a I indicator a I of omega for or omega n omega where a I are non-negative for I equals 1 2 dot 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 n and a I belongs to f for I equals 1 2 dot n. So, that is the definition of a simple function. Okay. So, a simple function is first of all a non-negative function which can be written as a finite sum, a finite weighted sum of indicators. Okay. So, that is what a simple function is. So, in particular, so for an example, if you want to take let us say, so let us say your omega f mu is simply, so let us say my omega f is simply r Borel. One example of a function which is simple will be, let f is equal to indicator of the interval 0 1 plus some other constant, let us say square root of tau 2 times indicator of rationals. Okay, this is an example of a simple function. Okay, I just made something up. So, this says, so you have a finite sum of some finite weighted sum of indicator functions. This is an indicator of the 0 1 interval and this is an indicator function of the rationals, right, and I have put some weight here. So, any non-negative weight will do. Okay. So, this is an example of a simple function. So, if I give you some omega, let us say I give you omega equal to half. Okay. What will my f of omega be? Half lies in this interval. So, this indicator will fire. Is half rational? It is. So, this will also fire. So, the value of this function will be 1 plus square root of 2, and if I give you omega equal to let us say 1 over square root of 2, then the value of the function will be 1 because this will not fire then, right, and if I give you omega equal to pi, the function will be 0, right. So, all that is needed is that these AIs, these sets here must be f measurable, in this case Borel measurable, right. So, I can even have crazy sets like Cantor sets here, right. So, is this understood? So, this is an example of a simple function. Plotting this is a little difficult. So, indicator 0 1 we know how to plot, it just takes the value 1 in the interval 0 1 and it takes values 1 at square root of 2, right. This guy takes value square root of 2 at all rational points and you have to plot the sum of the two functions, right. So, it is a little bit tricky to plot. If this set were also an interval, you can easily plot it, right. So, if for example, if I want to plot some simple function, so let us say, so that is one example, let g equal to some, so let us say indicator of 0 1 plus 3 by 2 times the indicator of 1 3, okay, for whatever reason. This is the reason I am considering this is very easy to plot, right. So, this will look like, so if I plot g against omega, omega by the way is simply from the real line. Now, I will get, so that is my 1, that is my 2, that is my 3. I will get, okay. So, I will get something like that, plus in the interval 1 to 3 I have the value 3 by 2. And 0 everywhere else, right, except at this point what will happen, because both are closed I will have the value here sometime 5 over 2 or something, right, it does not matter. So, this is 1, that will be 3 by 2. See, now you will realize that the representation of G in a certain form is not unique. So, this is my function, this is the function I have plotted. You could just as well write this as indicator of 0 to 3 plus half indicator of 1 to 3 or something like that. Is that the same thing, right? The same function as that, right, or you can write indicator of 0 to 1 plus 3 by 2 times indicator of 1 to 2 plus 3 by 2 times indicator of 2. So many representations are possible, right. So, they are all, it is all the same function, but multiple representations in terms of simple functions is possible, right, multiple representations are possible. Now, just to fix ideas we will say that a particular representation is canonical if these little ai's are distinct and big ai's are disjoint. Okay. So, canonical representation. So, there are multiple representations, right. So, we are going to say that I am going to consider canonical representations where little ai's are distinct and capital ai's are disjoint. Okay. So, in this, for example, this function if I have to write it in the, by the way the word canonical just means standard, okay, canonical just means standard representation. Okay. So, this for this function for example you want small ai's as distinct and big ai's as disjoint. So, I will write it as indicator of, so the canonical, neither of this is canonical. Why? This disjointness does not work, right. So, you will write it as the indicator of 0 to 1 open at 1, then indicator of the singleton 5 over 2 or something times the indicator of the singleton plus open 1 close 3 indicator of this whole interval, right. Similarly, you can think about what it should be here. Okay. So, that is called the canonical representation. So, from now on I will assume that when I write a simple function f of omega equal to sum over a of omega, I will assume that it is already in the canonical representation. If it is not in the canonical representation, you can put it into the canonical representation, right. So, that is not a problem. Now, I am going to define integral f d mu for a simple function. Okay. definition. Mu for this function is defined as follows. It is defined as so integral f d mu is defined as sum over I equals 1 to n a I mu of a I. Okay. Now, why is mu of a I well defined? A I is a f measurable. So, mu of a I is well defined, and this sum is, so mu of a I is some non negative, say bunch of numbers, a I is already non negative. So, and this is a finite summation. So, this is perfectly well defined, right, no problem, right. So, integral f d mu is defined as that. Okay. So, this is definition. Okay. So, for example, in this case what will that give you? So, if I consider not just, so if I consider omega f mu to be r b r lambda. So, I am considering integration with respect to measure mu, where mu is Lebesgue measure. So, integral of this g will be, so it should be 1 times the measure of this, which is 1, plus 3 by 2 times the measure of, so 3 by 2 times 2 plus whatever value, that is 5 by 2 times 0, right. So, you effectively see that you get the area under this. So, you will get, so what I just spoke out is just the area under this function, correct. So, what looks like some weird definition is, if for the case of the Lebesgue integral, when mu is Lebesgue measure, you get the area under this simple function, right. So, if you integrate this function with respect to Lebesgue measure, what will you get? You will get, what will you get? So, you will get 1 plus 0, right. See, one thing you should note is that this integral does not really depend on whether you have a canonical representation or not. Okay, that is something I have said, that let f has some canonical representation, but it does not matter. Even if you do not have a canonical representation, the integral's value will be the same. For example, if you have some other, so if you have, so that was not canonical, or this, say this is certainly not canonical, right, but in this case also you will first get 1 times 3 plus half times 2, which will be the same value, you can check. Okay, so, it does not really matter whether I am writing things in canonical representation or not. Okay, it is just for, I mean, it is just for the sake of definiteness. So, this is not, so this statement is totally unnecessary. You can check that this definition is the same for even non canonical representations. Okay, so you can just check that this is the same. So, examples 1. So, for that function over there, integral f d lambda will be 1 times 1 plus square root of times 0, which is equal to 1. So, the integral of this function is 1. Similarly, for g, integral g d mu g d lambda, that guy is equal to, I can write it as 1 times 1 plus 3 by 2 times 2, right, 3 by 2 times 2 plus 5 by 2 times 0, that is okay, that is also, that is 0. So, this is equal to 4, isn't it. So, that is, you are getting that area, right. So, this we have defined a simple integral So, integral for a simple function which corresponds to, at least when lambda is Lebesgue measure, it corresponds to area under that simple curve, simple function, right. So far so good. So, of course, if the measure mu is some other measure, you will not get the area under the curve, not at all, right. So far okay. Okay, so let us now, so do I have 5 minutes? I have 2 minutes I think. Let me try and do one another nice example. Well, actually I did that example kind of. So, I have, let me consider the following function called Dirichlet function. So, Dirichlet. So, you have, let us say omega is 0 1 and I am going to consider Borel 0 1 and lambda. So, this is my space, okay, and define let f of omega is equal to indicator of q intersection 0 1, q intersection omega, okay. So, this is equal to 1 if omega is rational and 0 otherwise. So, this is called Dirichlet function, okay. So, it is simply the indicator function of rationals in 0 1, okay. So, what I want to illustrate is, so it is clearly integral f d lambda is equal to what? F d lambda is equal to 0, right. This is the Lebesgue integral. So, the Lebesgue integral is very trivially 0, right. Now, what the reason I am doing this example is, even for such a simple function, the Riemann integral does not exist. You can show that the Riemann integral will be undefined, does not exist. Okay, do you see why that is the case? So, this Dirichlet function is discontinuous everywhere, right. It has so many jumps. So, in any vicinity of a point, so if you are at a real point which is not rational, it will be 0, but in its very close vicinity there will be a rational. So, there the function will jump to 1, right. So, it has, it is discontinuous everywhere. So, if you try doing the, so if this is my 0 1 interval, if I, so no matter what partition I consider, no matter how fine a partition I consider, in that partition the supremum of that function will always be 1, correct, and the infimum of the function will always be 0, right. So, my upper Riemann sum will be what? Will be 1. The upper Riemann sum is always 1 for any n, lower Riemann sum is always 0. So, limits, so the upper Riemann integral exists and it is equal to 1, lower Riemann integral exists, it is equal to 0, but they are different, the limits are not the same, right. So, the function is not Riemann integrable, whereas the Lebesgue integral is simply 0, right. So, you already see why I said the Riemann integral is actually quite an awkward integral, right, because it tries to look for too many details on where the function is in these little intervals, right, whereas this only considers measures, the Lebesgue integral only considers measures, right, it is defined in terms of the measure of certain sets, right. The Riemann integral is undefined. Okay, so, this function is not Riemann integrable, but it is Lebesgue integrable and the Lebesgue integral is 0, right. But of course, in nice cases like this, the Lebesgue integral and Riemann integral will both exist and it will coincide, right. Yeah. So, I will stop here today.